Okay, so you might be thinking that first stuff was a little bit interesting, but how does it link together with real calculations that we're going to do with these bigger numbers? Well, the key that connects all of it together and brings it into one unified, usable set of rules is the concept of place value. Now, I'm not going to spend a lot of time going over place value because I'm sure we're all pretty familiar with it. But we're going to look at before the decimal point right now. So we work backwards from right back to the left. Of course, this first place value here before the decimal point is the ones, and then tens and hundreds. Those are our three place values, and they are repeated over and over again. Ones, tens, hundreds, ones, tens, hundreds, and so on. Now this first group is our base group. We don't usually name them. This second group is the thousands group. And of course the third group is the millions group. And when we name a place value, we name the place value and its group. So this would be just the tens group. This would be the 10,000s group. Then the 10 millions group, and so on. When we put a number in here, like that, we usually go one group at a time. 23,000. So we read the thousands group, and then we read the base group, 781. Now, I'm not going to insult you by putting numbers up here and telling you how to read them, doing a lot of examples of that. But it is important that we see the place values and the numbers linked together, because what we are used to writing for that number, 23,781, is an abbreviation. It is a shortcut. Just like most of what we have been taught in math, it's a shortcut. The full form of that number, what some of you are taught as the expanded form of the number, would be 2 10,000s plus 3 1,000s plus 700s plus 8 tens plus 1 1. That is the full number. And when you see it written out in its complete form like that, a lot of the things we're going to discuss make a lot more sense. So I'm not going to spend a lot of time. I mean, there's a couple homework questions where you do have to take a number into expanded form. I'm not necessarily concerned that you can do that, but I'm going to do it a lot in our lectures so that you can see how the rules apply to the numbers. Because those place values, the 1,000s or the hundreds, are just as important as the digits, the numbers themselves, and how we do things. In fact, realistically, we don't even have to write that out in that order. Let's say I have 826. There is nothing stopping me from saying that that is 2 tens and 6 ones and 8 hundreds. Now, we don't usually write it that way. Why not? Yeah, because we go, it's not the normal way. We go from the largest digit to the smallest. Why do we always write it as 800s plus 2 tens plus 6 ones? Well, yeah, because it allows us to make this into a shortcut. It's what we call descending order. Going from the largest place value to the smallest. If we always do that, well, then it allows us to eliminate these place values and put it in just 826, 800s, 210s, 61s. This, by the way, is where the 0 came from, is the need to write it in an abbreviated form. Because what if we have 300s and 9 1s? I can't abbreviate that without this mystical 0. The 0 is actually a relatively new concept in math. But I can't write it as 3 9 because that wouldn't work. I have to have a 0 in there holding the tens place so that that abbreviation makes sense to me. When we get into algebraic numbers, all of this is exactly the same, by the way. We'll talk about that a little bit. It's going to be a couple weeks before we hit it. Well, actually, a couple days before we hit it in the summer session. So how does all this help with our calculations? Well, there's a few places it helps. The first place is with our rounding. If I give you 248 and ask you to round to the nearest 10, what's that asking us to do? Well, most of us look at that and say, well, to the nearest 10, that's 250. But what is it really asking us to do? When we're rounding, we're looking at a number line. When we're asked to round that to the nearest 10, what it's telling us is that we have a number line that is numbered by tens. Like that. And it's asking if we put 248 on there, which would be somewhere in here, which 10 would it be closest to, nearest to? Well, obviously it's closest to the 250. So rounded to the nearest 10, that is 250. So it's actually asking us physically on the number line, which one is it closest to? Now, when we go to round, I don't expect you to draw out a number line every time we round a number. That would be pretty tedious. So there's shortcuts that we've learned to do. 248 to the nearest 10. The first thing we do is identify the tens digit, which is the 4. Now the number that really tells us what to do is the next number. We look at the next smaller place value. That's an 8, which tells us we round the 4 up to a 5. How do we know? Well, because 1, 2, 3, and 4, if that digit was a 1, 2, 3, or 4, we would round it down to the 240, the next lowest 10. 6, 7, 8, and 9 are obviously closer to the next one up. Now 5 is right in the middle. What do we do with that? We've been told to round it up. If this were 245 to the nearest 10, we've been told when you see that next digit's a 5, you round it up, 250. There's a couple of good reasons for that. The biggest one is this. Let's say I have 5,752, and I want to go to the nearest 100. Well, my hundreds digit is the 7. The 5, of course, tells me to round up. Now, technically, that's saying I have a number line that's numbered in hundreds. I got 5,700, 5,800. Right in the center of that would be 5,750. But this is 752. The reason that we normally round up when that next digit is a 5 is generally there's something that comes after it, which means we are past the halfway point. We are further than halfway to the next 100 or next whatever place value we're rounding to. So it makes sense that this rounds up to 5,800. Now here, where there was nothing after that next digit here, it doesn't necessarily make sense whether to round up or down. So we've just adapted that rule that you're going to round it up always when you see a 5. If any of you go into mechanical design or mechanical engineering, there are times when you would round a 5 down, but I'm not going to get into that here because I don't want to confuse you. But there are special applications out there where, because of errors and buildup of errors, you do sometimes round them down. But for our purposes, if that next digit is a 5, you will always round it up. Now to the big deal with those place values, our operations. If I have 327 plus 462. Before I add these, I'm going to go ahead and write them out in their full form. So this would be 300 and 2 tens and 7 ones. This here, the 462, is going to be 4 hundreds and 6 tens and 2 ones. When we add or subtract numbers, what were we told that we had to have? Same name. Good. That goes right down to the individual digits. You see here that each digit, this isn't really just a 2, it is 2 tens. Each digit has a count and a name. Since we can only combine with addition and subtraction things that have the same name, I can only combine these 2 tens with other tens, like the 6 tens. That's why we've always been told that you have to be careful to line up the columns when you add, because we can only add or subtract digits that have the same name or same place value. Now that I have that, of course, I can just go ahead and do 300s and 400s is 700s. 2 tens and 6 tens is 8 tens. 7 ones and 2 ones is 9 ones. So it's 789. Now some of you might be looking at what I just did and thinking, he did that backwards. I went left to right. We're used to doing things right to left, starting over here and working this way. Why? Okay. In case something comes up to be more than 10, so we can carry it. If we run into something like this, 574 plus 259. I'm not going to write this out in full form, but I am going to go right to left like you're used to. We start out over here because we got 4 plus 9 is 13. I can't have a 13 in a single place value, can I? So I keep the 3 ones and I carry the 110 into the next place value. So 1 and 7 is 8 plus 5 is 13 again. So I keep the 3 tens and I carry the 100 into the next place value. 1 and 5 is 6 plus 2 is 8, giving me 833. This process that I just did, of course, is called carrying. And I'm going to assume that that's the way most of you were shown how to do it. There are, however, other ways to add. In fact, that process of carrying is only about 150 years old. Before that process was developed, addition was taught something like this. 5 plus 2 is 7. 7 plus 5 is 12, so we'll put the 1 down here. 4 plus 9 is 13, we'll put the 1 down here. 833. Carrying happened after we added, instead of during. So this again is a shortcut. It's quicker, it takes less space, and I don't expect any of you to change how you add. But just to be aware that just because you don't do it exactly the way a textbook tells you doesn't necessarily mean you're doing it wrong. Now, I'm a realistic person. I understand that most of you, after we go through this, are not going to do a lot of three-digit addition by hand. that most of you, since you have it, are going to use the calculator. But what I would hope is that you look at this here and say 574 is about 600, 259 is about 300. I'm expecting an answer around 900. Now, even in this estimation, you got 300s and 600s. Combine the counts, keep the name to get 900s. So that before you punch numbers on that calculator, you have an idea of what you expect the answer to be. Because if you're like me, I have these big sausage fingers. And when I hit my buttons on my calculator, sometimes I hit 2 of them, or sometimes I think I hit it and it didn't register. It wouldn't be uncommon for me to punch in 574 plus 259 and get an answer like 2,633. If I'm not paying attention, and you might chuckle, but I've seen a lot of students do this, just write down the answer and keep going because that's what the calculator said. It's got to be right. So be careful. Always know about what you expect your answer to be. Well, let's look at subtraction. So if we have 649 minus 236. Again, I'm going to write those out in their full form. So 600s plus 4 10s plus 9 1s, and 200s plus 3 10s and 6 1s. Now, we haven't really looked at subtraction at all yet, other than to say that it follows the same rules as addition. And it does. We can only combine things that have the same name. So once again, I can only combine the 4 10s with other 10s. So the 3 10s. And that's why in subtraction, just like addition, we've always been taught that you have to line up those columns and keep them straight. So I can go ahead and do this. 6 minus 2 is 400s. 4 minus 3 is 110. And 9 minus 6 is 3 1s. Now again, I went backwards, didn't I? That's the right answer, but normally we start on the right side and work back to the left in case we have to borrow. In case we subtract something, we get a negative number, we have to borrow from the previous digit. For example, if we had 536 minus 297, we would start from the right and work our way backwards. 6 minus 7 can't be done, so we're going to have to make the 6 bigger by borrowing from the 3. The 3 becomes a 2, so this is now 16. Because what we borrowed from there was 10. We borrowed a 10. So 16 minus 7 is 9. 2 minus 9 can't be done, so we're going to borrow from the 500. So this is 4 hundredths. Each of those hundreds, though, is 10 tens, so this is now 12 tens. 12 minus 9 is 3. And 4 minus 2 is 2. That's the way I'm assuming most of you were taught how to subtract. And it's the way I'm assuming you'll keep subtracting. But just like with addition, there are other ways to subtract. 150 years ago or so, this would have been taught like this. Well, 5 minus 2 is 3. 3 minus 9 can't be done, so we're going to borrow from the 3. That's a 2, and this is a 13. So 13 minus 9 is 4. 6 minus 7 can't be done, so we'll borrow from the 4. It's a 3, and this is a 16. 16 minus 7 is 9. We get the same answer. But this one actually makes a little more sense to me because when we borrow, we're not really borrowing from the 3 here. What we're really borrowing from is the solution at the bottom of the tens column. So it makes a little bit more sense to actually be taking it away from here than it would be from up here. This is just a shorter way to do it. Takes less paper, a little quicker. And again, it's how you were taught, so I'm going to assume that you'll probably keep doing it that way. In fact, I'm still the realist. I realize that many of you will, once you get to 3-digit subtraction, will probably turn to the calculator. I just ask that you look at this and say, okay, that's about 500. That's about 300. When we subtract 500s minus 300s, should be 200s. And we're expecting an answer around 200. So the 239 makes sense. If you got something like a negative 1,423, you know something went wrong. The big point is the calculator isn't evil, but using it blindly can be. Well, let's look at the next operation here, multiplication. Remember, multiplication is where the rules change a little bit. So let's do this, like 31 times 23. And I'm going to write these out in full form again. So this will be 3 tens plus 1 1 and 2 tens plus 3 ones. And when I multiply, I don't have to have the same name. So this 3 ones here can multiply the 1 1, but it can also multiply the 3 tens. In fact, every digit from one number can multiply every digit from the other number. And our process of long multiplication is nothing more than an organized way of doing just that, of taking every digit from one number and multiplying every digit from the other number by it. So the way we set it up, we usually start with the bottom number and its last digit, which is the 3 ones. And we do 3 ones times 1 1, which is, well, 1 times 3 is 3. Ones times ones is ones. It's positive, so we're going to put a plus there. And then we can take the 3 ones times the 3 tens, multiplying the counts. 3 times 3 is 9, but we have to remember to multiply the names. Ones times tens is tens. Now that we're done with that one, we can move over to the 2 tens. Now we were always taught, what do we have to do when we move over to this digit? Down here we either have to leave a blank space or put in a 0. Why is that? Well, it's going to become apparent here in just a second. So we do the 2 tens times the 1 1. 2 times 1 is 2, but we have to remember the place values. Tens times ones is tens. Putting them at 0 just help us line up our same names, keep our place values lined up. That's a positive, so put in a plus. Then our 2 tens times our 3 tens. 2 times 3 is 6. Tens times tens, hundreds. And now, of course, we see that we have the 9 tens and 2 tens can combine to make 11 tens. So 1 to carry the 1. So adding 1 to the 600s makes 700s. We get 713. So that process of long multiplication is done that way because when we multiply, we don't need the same name. So we can and we have to multiply every digit of one number by every digit of the other number. Now again, on the realistic side of things, I do understand that there's going to be calculators involved. But again, I would expect you to look at this and say that's about 30. And that's about 20. Now when you estimate with multiplication, it's a little different because we have to combine the names. This is 30 times 20, 3 tens times 2 tens. Well, 3 times 2 is 6, but tens times tens is hundreds. The shortcut we were taught was to count 1, 2 zeros in the problem. Have to be 2 zeros in the answer, right? Combine the zeros. Be careful with that, though. The one warning I'll put out there is this. $500 times 20. Got to be careful because I do 2 times 5 is 10. that 0 doesn't count. I still need 1, 2, 3 more zeros after it. So be careful if you're using that rule for estimating with multiplication. Okay, so that's multiplication. I take a little bit of a breath here because division is the one operation that I think has been changed the most when we look at how we do it and what it really is. To define division, we go back to what I said back at that first hour, where I said division is the same as multiplication, just done in reverse. So let's look at multiplication a little bit closer. When we first learned how to multiply, back around first or second grade, before we memorized our multiplication tables, before we knew that 5 times 3 was 15, how did we figure that out? There you go. We were taught to do 5 plus 5 plus 5. Oops, plus 5. Repeated addition. 5 times 3 meant we were adding 5 together 3 times to get 15. Well, if multiplication is repeated addition, division is repeated subtraction. If I have 24 divided by 6, what that is really asking me is, how many times can I subtract 6 from 24? Well, if I subtract it once, I get 18. I subtract it a second time, I get 12. I subtract 6 a third time. Subtract 6 a third time, I get 6. I subtract 6 a fourth time, I'm at 0. 24 divided by 6 equals 4, because I can subtract 6 from 24 4 times before I hit 0. In fact, if I have something like 13 divided by 5, I can subtract 5 once to get 8. Subtract 5 again, I get 3. Well, can I subtract 5 anymore? Not unless I look at the negative numbers, can I? So 13 divided by 5 is 2 with a remainder of 3. That's saying I can subtract the 5 twice, and there's going to be 3 left over after I subtract it twice. With that in mind, let's look at a long division problem. Let's do 21 into 69,439. Well, we just said division's repeated subtraction, but I am not about to start subtracting 21 from 69,000. I don't have that kind of free time. But there are some tricks I can do to make it quicker. And this is what long division was all about. Rather than subtracting 21 once, I can subtract it many times at once. How many times? Well, I have to try it and see. And what I try is the place value of this digit here. What place value is that? 10,000s, right? So that's where I start. That first place value of the number I'm dividing is 10,000. If I take, not 10, but 10,000 times 21, I get 210,000. Can I take that away from the 69,000? No, that's too big. It's bigger than 69,000, isn't it? So I can't take that away. So that doesn't work. So I move on to the next place value, which is 1,000. Well, 1,000 times 21 is 21,000. Can I take that away? You bet I can. I can take 21,000 away. I'll do it the full way. I won't take shortcuts. That would be 48,439. This would be 27,439. And I can subtract it again to give me 6,439. I could subtract 21,000 1, 2, 3 times. Now in reality, I wasn't subtracting 21,000 3 times. I was subtracting 21 1,000 times 3, or 3,000 times. This was 1,000 times. This was another 1,000 times, and another 1,000 times. So I know that I can subtract 21 from 69,439 at least 3,000 times. But right now there's the 6,439 left over. What do I do with that? I move on to the next place value. The 4 is in the hundreds place. So we try 100 times 21, which is 2,100. Can I subtract that from the 6,000? You bet I can. I can subtract it once. I can subtract it twice. And I can subtract it a third time again. So again, I didn't really subtract it 3 times. I subtracted 2,100 3 times. What I was really doing was subtracting 21 100 times 3, or 300 times. So I subtracted it another 300 times. Well, the next place value would be tens. So 10 times 21 is 210. Can I subtract that from what's left over? No, I can't. So we move down to the next place value. 1 times 21 is 21. Can I subtract that? I sure can. So I subtract 21, get 119. Subtract to 21 again, I get 98. And I keep going. Until I hit 14, where I can't subtract 21 anymore. I just subtracted the 1, 2, 3, 4, 5, 6 times. That's 1 times 6, so it was just 6 times. So it's another 6 times here. So 3,306 times, with a remainder of 14. So 69,439 divided by 21 is 3,306 with a remainder of 14. Now, for some of you, that might have been kind of confusing because that is way different than what you are used to seeing done for long division. I'm going to show you the normal way of doing it, but realize that this was the original long division. Everything we do or you have been taught has been an extreme shortcut version of this. So I'm going to erase my answer here, and I'm going to put what we've been taught for long division right beside it. And I'm actually not going to do our shortest version of long division. I'm going to do kind of the intermediate version. What we were taught was to do this. Can 21 go into 6? No, so we leave a blank spot above the 6. That's like saying we can't do it 10,000 times. Can it go into 69? Yes, it can. How many times? 3. So we put the 3 above the 9 because that was the last digit we used. 3 times 21 is 63. Well, you notice, really, this is a 3,000, and this is 63,000 that we're subtracting. It's the same process. We just took all the zeros out, and instead of subtracting the 21,000 several times, we did the 63,000 all at once. So 69 minus 63 is 6, and then we bring down the rest of the number, 439. Now we look at 21 doesn't go into the 6 anymore, but it does go into 64 3 times. The 4 is in the hundreds digit, so that 3 goes in the hundreds place in our answer. 3 times 21 is 63 again. Again, you'll notice we're just leaving out the zeros there. 64 minus 63 is 1. We bring down the rest of the number. 21 goes into 139. Well, first of all, it doesn't go into the 1 again. Does it go into 13? No. Now the 3 is in the tens place, and we haven't filled in the tens place yet, so we're going to put a 0 there. Then 21 goes into 139 6 times, which is 120. Did I subtract something wrong over here? Yep, this should have been an 8. I messed up already on the first day. So this would have been a remainder of 13, not 14 on that one. So anyway, there's 13 left over. So 3,306 with a remainder of 13. You can see one of the reasons why they shorten this process. First one is this takes a lot of paper. 2 is by subtracting over and over again, you open yourself up to that possibility of an error. Having to subtract the 21 6 times, I screwed up once and the whole rest of the problem was off by 1. So this is a shorter and generally less mistake-prone method. But if you're stumped and you don't remember where this came from, going back to the roots of long division, at least it makes the steps we do here make sense. We know why we do it that way. Because we're not really subtracting 63, we're subtracting 63,000 or 21,000 3 times. Now, long division, just so you know, is the one operation that I don't do by hand if I can avoid it. So I honestly expect that you guys are going to do these mostly with the calculator. So again, I would hope that you would look at this and say, hey, that's about 70,000. This is about 20. 70,000 divided by 20. Well, this gives us an interesting estimation problem here. Let's look at some division estimates here. If I had like 8,000 divided by 400. When we divide, just like multiplication, we combine the counts and we also combine the names. Only combining the names, we're using division. So combining the counts, 8 divided by 4 gives us 2, but this is thousands divided by hundreds, which would be tens. The shortcut is you cancel the zeros. There's 2 zeros here, cancel out 2 zeros here, and you're left with 1. But the example we just saw up there was 70,000 divided by 20. The 7 can't be divided by 2, can it? So what we do is this. You put a 0 with it. Can 70 be divided by 2? Yes, it can. 70 divided by 2 is 35. But now we have to be careful. This 0 has been used up. We're only working with these 3 now. Cancel out 1, 3,500. So that tells us when we estimated this one up here, we're expecting something close to 3,500. 3,306 is close enough for us to feel at least we're on the right track if we punch that in the calculator. Any questions? Again, I realize I showed you alternate methods for each of the operations. I hope that didn't confuse you, but at least maybe it'll lead you to a little bit more of an understanding as to where they come from. Now, there are other operations out there. One that we don't think of is this one here. What's that mean?
Third power.
8 to the third power. And how would we calculate that? Yeah, that is repeated multiplication. That little 3 there is saying that we have 3 of these 8s multiplied together, which would give us 512. Well, first, if you don't have that memorized, that 8 to the third power is 512, how would you do it on your calculator? Well, you could do 8 times 8 times 8, and that probably would work out okay for you. But what if I give you 2 to the power of 12? You're not going to sit there and do 2 times 2 times 2, and okay, did I do that 11 or 12 times? It is 4,096, by the way. But how do we get that? Well, most of your calculators. How many of you have your calculators so far? Are you still looking for some? The best calculator for this course is like the TI-30. They're about 12 or 13 bucks at most of your discount stores, and they do all the functions here and a whole lot more. But they're the simplest ones to use. If you already have a different one, like the Casios and the Sharps, the scientific calculators do the same things. If you have a graphing calculator that you want to use that you had to have from high school or something, you're welcome to use it. The one thing that the graphing calculator does not do well is fractions. So we'll look at how to do each of these things on the calculator as we hit them. Depending on the type of calculator you should have, one of a few different keys. Most of the scientific and graphing calculators have a key that looks like that. It's called the caret key. On the TI-30s, if you have the 2-line display, off on the left side about halfway down. If you don't have that key, you might have either a Y to the X or a X to the Y key like that. If you have the TI-30 1-line display calculator, that's on the right side, either the second or third key from the top. And all these keys work the same way. If you have a Sharp or a Casio, you may have one of those 2 keys, or you may have a key that looks like this. An X with a gray box up there or an empty box up there means the same thing. Or you might even have this one where it's just 2 empty boxes set up like that. No matter what key you have to enter this, you would press 2, then hit whichever key is your power key, type in 12, and hit equals, and it better give you 4,096. Well, what if we have more than one of these operations to look at? What if we have a problem like this? Well, some people might look at that problem and say, well, it's just like reading a book. I'm going to go left to right. So I start on the left. I do 5 plus 7 is 12. 12 times 2 is 24. Plus 6 is 30. Makes sense, doesn't it? Some people might look at that and say, you know what? I like to add first. So I'm going to do 5 plus 7 is 12. 2 plus 6 is 8. And then multiply. 12 times 8 is 96. And there's good reasoning behind either one of those, but they're different answers. And in math, we kind of like to have people look at a problem and get the same answer. And besides, both of those are wrong. In order to make sure that people do a problem the same way, in math we've defined something called the order of operations. Order of operations says when we have a set of numbers with no other information, in other words, there's no situation or context. In many cases, we'll have a story problem or we'll have a real life situation with the problem that'll tell us what needs to be done first. But in this case, we just had a list of numbers and operations. And if that's the case, the order of operations tells us what we should do first. The first thing we should always do is something called enclosing symbols. Many of you were taught this as just parentheses, but there are more enclosing symbols other than just parentheses. The second thing that needs to be done after we've taken care of enclosing symbols would be something called exponents. Exponents include two things. They include the powers that we just did, and they also include roots. Roots we haven't looked at, but we talked about every operation has a forward and reverse. The roots are the reverse of a power. 8 squared is 64. The square root of 64 is 8. It's the reverse of a power of 2. There are other roots other than square roots, but we'll look at those more later when we spend more time on it. So after we've done all the taking care of enclosing symbols and exponents, the next thing we look at is multiplication. And of course, multiplication and division are the same operation, so division gets done there as well. Then the last thing that we worry about is addition. And of course, subtraction is the same thing as addition, so it gets done there as well. So back to this problem we posed. 5 plus 7 times 2 plus 6. There are no enclosing symbols. There are no powers and roots. So the first thing that needs to be done is multiplication. 7 times 2 is 14. Now we have the 5 plus 14 and the 14 plus 6. Both of those are addition. Which one do we do first? Well, when we have more than one thing on the same level, then we do go left to right, just like reading a book. So we would do the 5 plus 14 first, which is 19, plus 6 makes 25. Well, let's look at something a little bit more difficult. So in here, first thing we see is that there are parentheses. We have enclosing symbols. So what that's telling us is we need to do what's inside that enclosing symbol, what's in that green box, has to be done first. Inside that green box, the order of operations still applies. Are there any other enclosing symbols? No. Are there any exponents, any powers or roots? No. Multiplication or division? Yes. We have 24 divided by 8, which is 3. So we still have the 8 plus and the minus 5. Now there's no more multiplication or division, so we have to do the addition and subtraction, and that, of course, will go left to right. 8 plus 3 is 11. Minus 5 is 6. Now, everything that was inside that enclosing symbol has been done. We're down to a single number in there. I could rewrite this problem now like this. And since we're down to a single number inside the enclosing symbol, I don't need the parentheses anymore. So I can just get rid of them. So they're gone. But I notice when I do that, there's nothing between the 3 and the 6 here. What do I have to put in there? Multiplication. Dot or X, whichever one works for us. Whenever we have a number outside of parentheses with no symbol between them, it is implied that that is multiplication. So now the enclosing symbols are gone. What do we need to do next? Well, there's no powers or roots, so back to multiplication and division. 3 times, and there's 2 multiplications, so we have to go left to right. 3 times 6 is 18. And then we would do the 3 times 2 over here, which is 6. And we're done with the multiplication and division. So now we have addition and subtraction. Again, there's more than one, so we go left to right. 6 plus 18 is 24. 24 minus 6 is 18. So all of this comes down to 18. I will tell you this, the single biggest mistake I see students make on this, and I'll catch a few of you doing it, is right from the beginning. First thing they do, they see this 6 plus 3 up there, they want to add them and make 9. We can't do that though because this 3 is multiplying something. We cannot add to that 3 until we have done the multiplication on that 3. That 6 can't get added in until way down here, almost in the very last step. So be careful with that. Let's look at something just a step more difficult yet. Something like this. So when we look at this, we start out looking for enclosing symbols, and we see that there's more than one here. As always, when there's more than one, we go left to right. Going left to right, here's our first parentheses, our first enclosing symbol. So we start with that. Where is its other end? Where's its other half? That can't be this one because that's facing the wrong way. This one here, that goes with this one back here. Here's the one that has to match up with that one. So that's our first step, is finding that first enclosing symbol and figuring out where it ends. So we have the purple box. So we have to start inside that purple box. But inside those parentheses, our order of operations still applies. And we see that inside there is another set of enclosing symbols. Another set of parentheses right here. So we have to start in there. Now before we start doing the operations, you'll notice on this one here, I did the operation and rewrote the problem every time. Well, I found that many people make as many mistakes rewriting the problem as they do with the calculation. So I'm going to show you a little bit of a shortcut here. At least what I do that helps me to not make quite so many mistakes rewriting the problem. I only rewrite it once in something that I can erase well. So whether it's in pencil in your notebook or whatever. So we said that we have to do, red is the color I use, this red box first. 9 minus 2 is 7. So I'm going to erase the 9 minus 2 and put in 7. Now I've reduced what's inside that set of parentheses to a single number, so I don't need the parentheses anymore. So I'm going to get rid of them. I'm going to get rid of the red box along with it. Do I need to add any multiplication symbols in there? No, I don't, because there's already a symbol on each side of the parentheses. So I didn't need to put in any new symbols there. We were already set. So now I'm back out. I'm done the red box. I'm back out to working in the purple box. No more enclosing symbols in there. Any powers or roots? Yeah. We got the 6 squared, which would be, you bet, 6 times 6 is 36. No more powers or roots, but I do have multiplication or division. 4 times 7 is 28. Down to addition and subtraction, so I'm going left to right. 36 minus 28 is 8. And 8 plus 1 is 9. So I've reduced everything inside that enclosing symbol to a single number. I don't need the enclosing symbol anymore. So I take out the parentheses. What do I need to remember to do? Put multiplication there because there was no symbol between the 5 and the parentheses. What would be next? Another enclosing symbol there. So I have to do the 3 plus 4 to get 7. And now that parentheses has been reduced to a single number, so I don't need it. Already subtraction here, so no need to put any symbols in there. Now I'm down to no more enclosing symbols. No powers or roots, so I'm going to multiply. The 5 times 9 is 45. 2 plus 45 is 47. Minus 7 is 40. The original problem looked like a bit of a monster, but as long as you go step by step, it's not too bad. We can also run into a little bit different twist on these problems. It looks like this. Like this. Now when we look at these problems, the first thing we have to figure out is, what does this symbol mean? Yeah, it means it's a fraction. What's it telling us to do? Well, it's called a fraction bar. We can think of fractions as a division problem. So it is telling us that we're going to have to divide. But it is also an enclosing symbol because it separates one part of the problem from another. So it is actually telling us that we need to do everything on top first. Then we need to do everything on bottom. And then we're going to divide those two results. So let's look at the top first. What would we do first on the top of this? The powers. 4 squared is 16. Then we would have to multiply 8 times 4 is 32, plus 16 is 48. So we've reduced everything on the top to a single number. So we're done on top, we need to work on bottom. On bottom, what would be the first thing we need to do? The root, the exponent. Square root of 4 is 2. Then we have to do the multiplication. 5 times 7 is 35. 3 times 7 is 21. I realize I'm taking some shortcuts with my notation here, but I think you guys can follow. Any questions where I came up with those numbers? Okay. Next, I subtract, add and subtract. 35 minus 21 is 14. And I have to add the 2 to get 16. So now I've done everything on the bottom of that fraction and reduced it to a single number. So now the last thing left to do is to divide. 48 divided by 16 is 3. So that fraction bar is a type of enclosing symbol. It's telling us to do one part of the problem first. something like this one. 8 plus 3, square root of 1 plus 9 times 7. Now we've seen that square root symbol a couple of times, but we're not terribly familiar with it. But here it's actually got a second purpose. It is also an enclosing symbol here. It's telling us we have to do everything inside of it first because it's separating that from the rest of the problem. So we need to do the 1 plus 9 times 7. Of course, we multiply first. Even inside an enclosing symbol, order of operations still applies. So 9 times 7 is 63. 1 plus 63 is 64. Now we've reduced everything inside that enclosing symbol to a single number. We can get rid of it. The difference is here, the enclosing symbol is telling us to do something. So when we get rid of the enclosing symbol, we must also do what it is telling us to do. The square root of 64 is 8. So getting rid of the square root symbol means we have to also reduce that 64 to an 8. So this is now 8 plus 3. Just like with parentheses, this becomes times. So now we can do the multiplication first. 3 times 8 is 24. 8 plus 24 is 32. So you can see the enclosing symbols are not just the parentheses that we've been shown. There's more to it than that. Some things that kind of pop up in notation that I want to make sure I wrap up before I let you go here today. Of course, we know this symbol, the equals symbol, just telling us that two numbers are the same, have the same value. 8 equals 8 is pretty obvious. 8 equals 5 plus 3. But one that some people struggle with, or ones that some people struggle with, look like this. If I have things that are unequal, what symbol goes in there? Is it this one or this one?
The top one.
The top one, exactly. This is the less than symbol. 6 is less than 9. How do we remember which one to use? Well, we were taught a lot of things when we were kids. One of my favorites was always the alligator. The alligator's hungry, so he eats the biggest number. So the jaws go towards the biggest number. But that's not really where it comes from. Where it comes from is this. The number line. Maybe we should space them a little bit better. What this is asking us is, 6 is on which side of 9? Here's the 9, here's the 6, it's on this side. That symbol there actually comes from this arrowhead of the number line. Okay? Enough of that. I think you guys have suffered enough for one day. I can definitely see the no vacancy signs coming on in everybody's eyes. So I'm going to cut it off there. You do have a homework assignment due for noon tomorrow. I'll be in here. For those of you in Rice Lake, I'll be in by 8:30. For those of the other campuses, if you think it would be helpful to turn on the network before the start of class at 9 o'clock, let me know and I'll have them do that for us. Okay? You guys have a good day. I will be here till about noon, so if anything comes up, if you want to work on stuff on the computer lab and come back in, you are welcome to.